Have you ever looked at your car and realized how desperately it needed to be cleaned? One of life's simple joys is spending a summer day washing your car and anticipating the freeing feeling of flying down the highway in a fresh ride. But gone are the days of dirty buckets of soapy water and smearing sponges. The modern technology of today's foam guns makes lathering a breeze, with the help of Bernoulli's principle. So we set out to create our own version of this principle in action. On the left side, we have a pump blowing air at a standard velocity into a nozzle. As the nozzle bottlenecks, its cross-sectional area decreases, which we know will cause the airspeed velocity to increase due to conservation of mass.
Listen, in order to maintain airspeed velocity, a swallow needs to beat its wings 43 times every second, right?
The increase in velocity should yield a decrease in pressure inside the bottleneck portion of the nozzle, causing the fluid resting in the open container to rise up the connecting tube. In short, we are looking at the relationship between the two areas or diameters that make up the nozzle and the distance h that the fluid travels in the tube. Here's our actual assembly. We 3D printed 3 different nozzles, each with a large opening of 15/16 that connects to the pump. The bottleneck diameters were 0.25 inches, 0.368 inches, and 0.476 inches respectively. The smaller the diameter, the greater the velocity of the air, the greater the pressure difference. By Bernoulli's, we can hypothesize that the distance traveled by the water will be greatest on our first test, when the nozzle diameter is the smallest. Note that the water level in the mason jar starts at 3 inches on the ruler for each test. Let's check out the math to explain why. The pressure at point 3 is less than P1 by a value of ρgh. P1 is atmospheric, so we'll call it 0. Then we also make the convenient assumption that P2 equals P3 due to the low density of air relative to water. In the Bernoulli equation, we say that P0 is 0, and the height z is the same at points 0 and 2. Make the hydrostatic substitutions, and we see that delta H is a function of our area ratio and the initial pump velocity. And by the conservation of mass, a greater ratio of initial to bottlenecked area should yield a larger bottleneck velocity, which is measured via the height change of the water.
And while our data shows that the correlation between these two metrics is positive experimentally, it does not yield the quadratic rate to be expected from the formula. This error might be attributed to the variances in the 3D prints, which had different levels of leakage at the tube connections. If you wanted to make a foam gun like the one at the beginning of the video, you just have to make sure that your delta H value is greater than the length of your tube.